Hello! In this video we provide an introduction and explain basics of Fourier series and frequency responses. We motivate our theoretical explanations with the experiment of observing certain characteristic points of a frequency response of a resistor capacitor or an RC circuit that you can see over here. The experimental setup consists of an RC circuit. Here is the resistor and here is the capacitor, a function generator, and an oscilloscope. The function generator provides input voltages that are filtered by the RC circuit. We use oscilloscope to measure the output and input voltages. Output is measured from the capacitor to the ground. The function generator is used to generate sinusoidal signals of different frequencies. By turning this knob, we can adjust the frequency of the signal. The oscilloscope measures both input and output signals. Channel 1 is the output signal and channel 2 is the input signal. So the main take-home message is, if a sinusoidal input signal is injected into an RC circuit at a given frequency, the output signal will have the same frequency with a certain magnitude and a certain phase angle relative to the input. So let us verify this experimentally. Remember that yellow signal is the output signal. We adjust the frequency of the input signal, and as we increase the input frequency, what can we observe? We can observe that by increasing the input frequency, the amplitude of the output signal decreases. Also, there is a phase delay between the output and the input signal. Vice versa, if we decrease the input frequency, we see that the amplitude of the output signal increases. So, the basic idea of Fourier series expansion is that we can represent almost any periodic function as a sum of harmonic terms. To translate this in layman terms, we can represent any function as a sum of sinuses and cosinuses. So what you can see here is basically the definition of Fourier series. F of t is a function of time, and on the right hand side you see these terms. Cm are coefficients which are calculated using equation 2, and this term can be represented as sum of sinuses and cosinuses. More precisely, we can represent the term ejm omega 0 t as cosinus of m omega 0 t plus j, where j is a complex unit, sinus m omega 0 t. So, if we have an analytic form of the function f of t, we can find the coefficient Cm and we can represent such a function using Fourier series. So let us see how the Fourier series expansion works in practice. So what can we see here? This is a periodic pulse function or a square wave function, and we want to represent this function using the Fourier series expansion. Now, the period of this function is 2 seconds. T is the period. Mathematically, this function is described as follows. A is the amplitude, and we leave a general form of the function where A can be any number. On the website, you can find the link of the website below. I have made a detailed derivation of the Fourier series expansion of this function, and it's given as follows. So, K max is the maximal order of the approximation. Omega 0 is a fundamental angular frequency. Omega 0 is 2 pi over t, and k is the iteration index. Now, for certain orders of approximation, that is, for certain orders of k max, we will get different approximation accuracy. So, in this graph, you can see what happens when k max is 1. In this case, we only have one cosinus here. Notice here that these are the coefficients. So these are the coefficients. So if k max is equal to 1, we only have one cosinus term here. And the function can be approximated as follows. Now, if k max is equal to 3, you see that the approximation accuracy improves. K max equals to 5, we get even better accuracy. And for k max equal to 10, the accuracy is really good. Let us now explain frequency response of a linear system. So, here is a system representation. This is so-called block diagram. U of t is an external input affecting the system dynamics, and y of t is the system output. Now, what is the system output? The system output is some variable inside of the system that we actually measure. There are several ways to mathematically describe the relationship between the inputs and the outputs. We can, for example, use differential equations to relate inputs and outputs. Differential equations can be used to argue about system stability, and by solving them, we can compute the system output for a given input. However, in many situations, we would like to have a simpler representation of the system behavior that can be used in some real-life engineering applications. One of such simpler representations is the system frequency response. To explain the system frequency response, we need to go back to the Fourier series expansion. So, we know that almost any periodic function can be represented as a sum of cosinus signals. Here, AI is a coefficient, omega I is the angular frequency. In our previous slide, we have denoted AI by SAI, but these are minor differences. So this is the general form of the input signal. This can be, for example, a step function, can be a function, sawtooth function, etc. Now, since the system is linear, right? The system response to sum of signals is the sum of system responses to these individual signals. So let yi be a system response to cosinus omega it. this cosinus. Now, since the system is linear, the response to u of t is the sum of the individual responses yi to these terms cosinus omega it scaled with the coefficient a. And this fact motivates us to ask the following question. What is the system response to a cosinus omega I t? Why this is important? Well, to repeat, if we know the system response to these individual cosinus omega t, then we can reconstruct the system response to almost any function u of t. And the frequency response is nothing less than the response of the system to cosinus or sinus signal where we change frequency omega. So before we explain frequency response, we need to introduce the concept of a transfer function of a dynamical system. First of all, we know that the output of the system can be represented as a convolution, this is the convolution integral, of the impulse response function and an input. So the impulse response function is nothing less than response of the system to the impulse function. So the impulse function has the following form. So now let us assume that the input is given as e to the power st, where s is generally a complex number, and t is time, of course. Now, substituting 16 in this equation, we can obtain the following equation, the equation 17. So the equation 17 tells us that the output can be represented as product of the function h of s, only a function of a complex variable, times e to the power s. The term h of s, defined as the following integral, is the system transfer function. So the system transfer function is a Laplace transformation of the impulse response. So if we know the impulse response, we can perform Laplace transformation and we can get the system transfer function. Let us now see what is the response of the system to the cosinus function. We will use the transfer function concept to show that the response is, again, a cosinus function with some delay and amplitude change. So the whole message is, if we have a cosinus signal as an input to a linear system, at the end we will have a cosinus signal with the same frequency, with some delay, and with some amplitude that is different, generally speaking, different than the input amplitude. So AI is not equal to A output in general case. Now, let us go back to the input AU cosinus omega t. Using the Euler's formula, we can represent cosinus as a sum of two exponential functions. And we can decompose input u into two inputs, u1 and u2. Now, u1 has the following form and u2 has a similar form, only with a negative exponential. Now, since the system is linear, the response to u function will be the sum of responses to u1 and u2. Here is the response of the system to u1 when we apply the previous formula for the transfer function and convolution. Now, On the other hand, transfer function, if we substitute S for j omega, is a complex number and it can be represented in the polar form, of course, where m is the magnitude and phi is the phase. Using this transformation, we can express 21 as follows. So if we put exponential function as an input, we will get the exponential function with some phase difference. Similarly, for u2, we get the following, and using the same reasoning, we get. To compute the system output, we have to sum system outputs for the individual inputs. And here's the expression. Now, this expression can be transformed in equation 26. Now, this equation 26 is a fundamental equation. This equation shows the following. First of all, the output when the input is a cosinus function with the frequency omega is again a cosinus function with the same frequency and with a certain phase lag. For example, this can be delay, and the amplitude of m of omega au. So we see that the amplitude of the output signal is a function of the amplitude of the input signal and m of omega, where m of omega is the magnitude of the transfer function. Now, m of omega and phi of omega are two functions that characterize the system frequency response. M, loosely speaking, m of omega tells us about how much the output amplitude will be amplified or attenuated compared to the input amplitude. And phi of omega is the phase delay. So let us now analytically derive a frequency response of an RC circuit, the example from the beginning of our video. Here is an RC circuit. This is the input voltage, this is the output voltage, this is the resistor, this is the capacitor. The differential equation describing the dynamics of the RC circuit is given as follows. Dot is the first derivative. T is product of RC and it's called the time constant. Now, taking the Laplace transform of the last equation, we obtain the following equation. And this equation, taking into account that we assume that initial conditions are zero, this is the initial condition and this is the Laplace transformation, we can derive the equation 30. So the equation 30 is the transfer function of the RC circuit. It is the first order system. To repeat, T, capital T, is a time constant. Now, by substituting S as j omega, we have the following form, the polar form of the transfer function, where we can immediately read the magnitude and the phase. So the magnitude and the phase are given as follows. So here's a numerical example of computing the magnitude response and phase response of the RC circuit. For codes and more details, see my website. We see that basically magnitude decays as a function of omega, and the phase decays again as a function of omega and reaches minus 90 degrees. Another concept that we need to introduce is the concept of the cutoff frequency. The cutoff frequency is usually defined as the frequency of omega at which the magnitude response is equal to 0.707. That is, compared to input amplitude, the output amplitude is 70%. Now, let us see what is the cutoff frequency of the RC circuit. By simple calculations, we obtain that The cutoff frequency is determined as 1 over RC. That is, T is the time constant of the system. Now, let us go back to the beginning of this video. And we were measuring the frequency response of the system. Now, here are the results. Here is the comparison between theoretical prediction and actual measurements for 330 ohm resistor and the capacitor with a capacity given as follows. We can see that there is a good match between the theory and the practice.